So in the previous two videos, we have told you that for simple means we can calculate it. We know its mean and the standard deviations. Okay, the mean would be the same as the population mean, and the standard deviation would be smaller than the population mean based on a formula with square root of n in the denominator. So these two values are important, but we need some more. We need to really know the distribution of simple means. We need to know whether it's normal, uniform, whatever. So that's the central topic of the next two videos. In general, if we sample from a normal population, then if the population is normally distributed, then regardless of the sample size, your sample mean would always be normal. Okay, so formally, if you have xi as a size n random sample from a normal population with mean mu and standard deviation sigma, then your x bar would be normal with mean mu and the standard deviation sigma over square root of n. So here you have three pieces of information: the mean of sample mean, the standard deviation of sample mean, and the distribution of sample mean. The first two are actually old. We introduced them in proposition 1 in the previous videos. Okay, so we already know that. What's new from the fact that the population is normal is that now the sample mean would also be normal. So mu and the sigma over square root of n, these two facts does not depend on your normal distribution, but to have a normal distribution for your random sample and for your x bar, you really need the population to be normal. Okay, that's something new for this proposition. So let's revisit our example 2. We know that the weight of a bag follows a normal distribution, and that's our assumption, with mean mu equals 2 and the standard deviation sigma equals 0.2. The quality inspection process is that they will collect 4 bags of candies and calculate the sample mean. We hope that the sample mean is within 1.8 and 2.2. So I want to find the probability that I am unlucky. So what's that? We now know the distribution of the sample mean x bar is exactly a normal distribution with mean mu and with mean 2 and the standard deviation 0.1. So once I have this information, then calculating the punishment probability is simple, right? Because this is a normal distribution, so that means I can have, for example, its curve. And then I know this is 2 and I have standard deviation 0.1. So when I need to calculate the probability for x to be less than or equal to 18, I know how to do it. For example, in Excel, you call that function NORMDIST, or in other softwares, you again can calculate this particular area. For x to be greater than or equal to 2.2, that's the same thing, right? You know how to do the calculation. So once you know the population is normal, then you know the sample mean is normal. Then you know how to do the calculation, and then you know what's the probability for us to be punished. With that, now we can even go further. So when we have this information and the sample size information, we can calculate the punishment rate around 5%. If that's the case, of course we may want to ask whether we should adjust our standard deviation of our population. Okay? Whether we want to pay more or less attention to the production process, whether we want to introduce new technology or hire more persons so that we can decrease the probability. So we hope that this punishment rate is small, right? We hope that we can decrease this probability of getting or this probability for our products to get returned, or the probability of getting fines, but that is costly, right? Because we need to also decrease sigma, and decreasing sigma, of course, is costly. So with this probability distribution, normal distribution, we can actually draw a curve like this. What's that? That's given any sigma, given any value of our population standard deviation, what's the probability for us to get punished? Okay, what we already calculated is that if sigma is 0.2, if the population standard deviation is 0.2, then the punishment rate would be around 4.5%. When this goes up, this will also goes up. When this goes down, this will also goes down. But we can see that to what degree we would like to do. Okay, we want to optimize sigma. In particular, if we improve sigma from 0.2 to 0.1/2, that seems to be helpful, right? Because from there, we can get an improvement on our punishment rate for around 3% to 4%. Okay, but if we do that further and cut down our standard deviation from 0.1/2 to 0.15 to 0.1, the cost would be very high, but the benefit is very small. It's very small. Okay, and what's the most important is that we can quantify the benefits and costs only if we know the distribution of our sample mean. If we do not know the distribution of our sample mean, we just cannot calculate these punishment rates, and then we cannot decide whether we want to further improve our production line or not. Okay, so sample mean and the the sampling distribution is really important to you in this decision-making situation. Very similarly, so we know that given these facts, the punishment rate is 4.5%. The quality control officer may actually also try to increase the sample size n, and as always, if we increase the sample size n, then that estimation would be more accurate, right? So that means the punishment rate would decrease. Why it decrease? Because mu equals 2 is actually an ideal situation. So my population mean is actually within 1.8 and 2.2. So that part is good. If the officer collect 4 values and claim that my production process is having some problems, then in some sense she is making a mistake or she is making an error, right? The officer should not say that, because in fact my production line has a population mean that is 2, so that is good. But still, it's possible for the sample to be so weird, and that means the officer may make a mistake. So that means if the officer want to reduce the probability of making a mistake, then she or he can try to increase the sample size. This should be sample size. And try to increase the sample size. And given any sample size, we can again calculate what's the probability of making an error. Then that's something we can use to decide the optimal sample size. Because increasing sample size is costly, but it gives you the benefit of not making mistakes about quality inspection. Okay, so that's also a very good thing. So now we have one general conclusion. When the population is normal and we sample from a normal population, the sample mean would also be normal. And as always, the mean and the standard deviation of our random sample mean will be mu and the sigma over square root of n respectively. So these are fine, these are good. But what if the population is non-normal? Okay, if the population is non-normal, can we say anything? Yes, we can. We have a very powerful theorem, which we call it the central limit theorem in statistics, that would apply to any population. Okay, so let's talk about it in the next video. Thank you.